So now let us welcome our third speaker, Dr. Arshad Nawaz. Nawaz received his PhD from Shanghai Jiao Tong University and is currently working there as a postdoc research. His research focused on control and optimal operation of modern energy systems. Today, he will present a talk, Advanced Hierarchical Control for Sustainable Reuse of Second-Life Batteries in Renewable Microgrids. Please join me in warmly welcoming Dr. Nawaz.
Hi everyone. Can you hear me?
Yeah, we can hear you.
Yeah, okay. I will share my screen. So my today I would like to discuss the battery related in microgrid. The topic is advanced hierarchical control for sustainable reuse of second life batteries in renewable energy. Uh, Is a background, we all know that in modern power systems, we are going towards green energy. In green energy, we have renewables like solar and wind. Uh, but the problem with these renewable generations is the uncertainty, intermittent and non-dispatchable factors. So for this reason, battery storage has been widely deployed to compensate for the renewable intermittency, maintain supply and demand, sometimes also used for frequency and voltage support. And especially in islanded mode, we need to improve the energy autonomy. However, the increasing reliance on the battery raises critical challenges related to the aging, degradation, and its reliability. These are the factors which are um, these are the issues with the battery system. Nowadays, a lot of let me explain the second life batteries. First of all, sorry, I didn't include this slide. We have second life batteries means the batteries which are already used and they are retired and they are reused for some purposes. And they have some kind of a storage capacity available, like 80% storage capacity. So those kind of batteries are referred to as a second life batteries. So the second life lithium-ion batteries, which are usually retired from electric vehicles, EVs, present a cost-effective and sustainable storage solution, which could be used for power system because they offer reduced capital cost, economical benefits, and environmental impact reduction. The problem with is that second life batteries is the battery is combination of different cells. They have a kind of heterogeneous state of health condition. They have internal resistance, which is like uneven. They have a different cell temperature. That's why they have thermal variability, and they have degradation behavior, which is not uniform. So usually the conventional battery system, they treat the battery pack as a single unit, homogeneous unit, and they ignore the cell level differences, which results in increased rate of aging, imbalances of voltage, and premature battery pack failure. Um, for the limitation of the current existing control strategy, which are used in microgrid controls, are actually they are a single aggregated system level dispatch ignores the inter-cell heterogeneity. Cell balancing techniques are reactive, not productive. Also, aging and thermal dynamics are rarely integrated into dispatch optimization. um, Multi-time scales interaction are not explicitly addressed. Um, there are no unified framework that simultaneously ensures microgrid power balance, also account for the cell level electrothermal dynamics of the battery, and its mitigate degradation, and also have multi-rate control actions, the coordination related to that. These gap uh, makes the heterogeneous second life battery pack a very critical problem. Um, a lot of techniques have been used to accommodate the second life batteries in the existing system, but due to the mentioned issues, they are not enough, and there are still these gaps are uh, existing. So for that, let's first explore the battery storage model, what it's look like. We have the usually, like we all know, related to the control methods in the energy management, that battery has a state of charge, which is the capacity of storing charge per cell, and it is given by mathematical model is like the power it can provide with the existing state of charge. So with this model, we have maximum and minimum constraints for state of charge, and also we have the constraint of power provided during discharge and the power which is used for battery charging. And the charging and discharging cannot occur simultaneously, so they are mutually exclusive. And for the degradation of the lithium batteries have two factors. They have cyclic stress and they have thermal stress. Cyclic stress arises from the discharge. When battery discharges, it loses some kind of its capacity. And also when the temperature is higher or it is lower. So on the under room temperature, it's work fine. But if the temperature is too high or if the temperature is too low, it's degraded storage capacity. So the state of health could be approximately expressed with this equation, which is the combination of cyclic aging and thermal aging. And the second equation is the temperature coefficient, and the last one is the capacity degradation. The C represent capacity. So when we have a battery power which is greater than zero, which means we are discharging, we are taking power, so the battery would degrade. If we are charging, then we have no degradation. So the capacity would be equal to capacity. So the power balance for the power system, we have a load and we have a renewable energy. So the net power is usually zero. So to achieve this, usually wind and PV, sometimes they are not sufficient to balance the load. So the net sometimes is non-zero. For that, we compensate that net power with the battery. This is a simple case we have taken. So for that, we have proposed a method to utilize the second life batteries in the power system. So the first encircle in purple, you can see that we have a system level MPC, and then we have a cell level MPC. Um, we have the for the system level MPC is actually looking, or the purpose of system level MPC is to achieve the net zero power supply. And then the cell level, actually it's accommodate for the voltage imbalances, the temperature and state of health. So with, you can see from the system level one that we are actually optimizing the battery power to meet the supply demand imbalances, and then to accommodate the imbalances inside the battery, the voltage, the current, and the thermal effects. We have a second MPC, which is cell level MPC. So for that, the battery power is a signal for a cell level MPC is a reference. Based upon that, we can accommodate the voltage imbalances by sharing the uh, charge between cells, and we can control the current, and we can accommodate for the voltage for the thermal temperature of each cells. So these two MPCs, they are actually working on different time scales. The system level is operated like 5 minutes or like 30 minutes, you can assume like that. In the cell level MPC, it is much faster as compared to system level to accommodate for the voltage imbalances, the current. So they have a multi-rate and they are following a hierarchy. The system level is actually providing a reference to the cell level to uh, accommodate its voltages, currents, so that the desired battery power could be provided to the system. So there is a coordination condition. You can see the battery power, which is the physically equal to the voltage times sum of the cell's current, which is the summation, plus a slack variable. The slack variable here we have introduced to accommodate for any kind of imbalances between power and load imbalances. So this is to soft the coordination condition as well. Uh, Here, the system level MPC, we have objective function, which is actually optimizing the battery power, the battery net, and we have a slack variable. Same, we have the constraint. We have the coordination constraint, which is the nominal voltage of the cells with the summation of the current of each battery cells. Battery is combination of different cells, so each cells are estimated and the summation into the nominal battery pack. So with this, we get the coordination condition, which is also a constraint, and this is provided to the system level, cell level MPC here. After getting the coordination condition, we have the cell level objective function, which is actually accommodating the battery cells, the voltage of the battery cells, the current, the state of health, and also the 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 last term, which is EIJ. You can see this is the energy um, exchange between different cells, because we have, as I mentioned, that in a second life batteries, the cells have different internal resistance, and based upon that, they have different storage capacity. So maybe and this arises to the voltage imbalances as well. So in order to regulate the voltage to a nominal uh, value, we need to share the energy storage between the cells. So the cell is transferring energy from one cell to another. The cell which has less capacity, it is actually exchanging the energy to the another cell which is more capacity or not more degraded. So this objective function is actually we are getting the optimal values for energy exchange, the current, and the voltage. Uh, in the voltage, average voltage is the average of all the cells. So for that, I can also add. I will go one slide back. I can show that the battery here, you can see these batteries are the combination of series and parallel combination. So we have a voltage and current as well. The simulation results you can see on the figure 2. We have a renewable generation, we have a battery dispatch, and we have a load. So the battery is performing perfectly for accommodating for the net imbalances, uh, and is we are we are using the adaptive pulse charging. So during the duration of discharge, the charge time, we are actually not providing it directly current, just because that not a constant current, just because we have different cells. So to safeguard the health of different heterogeneous cells, we are applying adaptive pulse charging, and this pulse charging is providing different rate of charge to different cells based on their health. And you can see it is each cells have a different charge pulses. And the figure 4, you can see the voltage of all the cells. They are almost achieving the nominal values, and they have a kind of a consensus to agreed on a nominal value, which is the average value. And the figure 5, it is the energy sharing between the cells of the battery pack, so that the voltage which is shown in figure 4, it should be maintained or regulated to the nominal values, which is like 3.4 and 3.8. Here we have the different cells thermal performances. The temperature is reduced due to these energy exchanges, the current sharing. The temperature is maintained between like 24 to 30. And figure 7, the state of charge. The With this method, the state of charge of each cell, and then the red line is showing the aggregated state of health of a battery power. It is degrading with much lower rate. So it's to compare that this method is working fine. We have compared this method without the with a method which is like treating the battery pack is a homogeneous system. So the degradation rate is much higher than is compared to the method which we have applied. And the figure 4 is the uh, error diagram for that. With that, we conclude our work. And as a conclusion, the framework, when we have combined the system level MPC with the cell level MPC, the performance of the degradation, battery degradation is much improved. The cells current with the adaptive like charging strategy, the system health is much better. And with the energy exchange, the voltage profile is much been improved. So the degradation rate is calculated due from the simulation. It is like reduced by 54% or 24-hour simulations. So in the future, we are extending our work to multi-system, multi-microgrid system, and multi-energy systems, where we can apply a real system, real batteries with more battery packs. For this simulation, we have used 16 battery packs, but sorry, 15 cells battery pack. So for the real system, the energy storage system has more battery packs. For example, like 100 to 500 cells are accommodated in a single battery packs. So based on that, we would extend our work to much more realistic scenarios. That's all for today, and thank you for listening.